Hi there, welcome to this video where we continue taking a look at Richard Dedekind's essay titled The Nature and Meaning of Numbers. This is the fourth video, and in this video we're going to be taking a look at chapter 4, or at least the first half of chapter 4. I don't think, because this is quite a long chapter, and I've been doing a video per chapter up to now, but this is quite a long chapter. And if you've watched any of my previous videos, you know that I'm usually quite I usually take a long time to say what I want to say. So this chapter is probably going to be split into two videos. So I'm aiming to get up to and including theorem 58 in this video, and then the next video from theorem 59 up to the end of the chapter, all being well. Okay, so hopefully you've watched some of my previous videos, or hopefully you've at least read the contents of the first three chapters of Dedekind's work. If you haven't, you might find the contents of this video a little bit difficult to follow. So I might be using some terminology that you're not necessarily familiar with. So it would be advisable for you to at least familiarize yourself with the contents, to a certain extent, with the contents of the first three chapters of Dedekind's work. Feel free to watch my other videos if it helps you to better understand Dedekind's work. But here we go. So as usual, I'm going to bring up on the screen the page that I'm kind of reading at a given time, and for the definitions, the theorems, and so on and so forth, I'm going to stop and I'm going to give some explanation, some interpretation, and just a reminder: whatever I say in this video and really any other video that I do on Dedekind's work, it's not definitive. It's merely my interpretation, which may or may not be correct depending on which way you look at it. So off we go then. So we start with definition 36. So chapter 4, by the way, is titled Transformation of a System in Itself. Definition 36 reads as follows: if phi is a similar or dissimilar transformation of a system S, and phi S part of a system Z, then phi is said to be a transformation of S in Z. And we say S is transformed by phi in Z. Hence, we call phi a transformation of the system S in itself. So this kind of relates back to something that I was saying. I just want to stop off there for a second. Something that I was talking about in the previous video relating to chapter 3, where when we've got a transformation, it depends on the context, really, what kind of transformations involved, and all kinds of things as to how specifically you need to kind of interpret the transformation that Dedekind is talking about. So in chapter 3, we had similar transformations, and in that chapter, it seems that Dedekind was viewing a transformation phi, a similar transformation phi, as really a transformation between a system S and its transform, phi S. Okay, so it might be that so this is something that I've talked about in the previous video. So this I'm repeating myself here. I'm aware. Phi S, the system phi S, which is the transform of S under the transformation phi, consists of all of those elements of the form phi S, where lowercase s is an element of the system uppercase S. Now, it might be that phi S is actually an element of a larger system than phi S. So we might have, for example, we've got the system S, we've got the system T, and then we've got phi S here as a part of T, maybe a proper part of T. So S is transformed into phi S via this transformation phi. Dedekind doesn't in chapter 3 at least, he doesn't seem to consider this transformation phi, which is to represent a similar transformation in chapter 3, as a transformation of elements of S into elements of T. He really seems to be considering the transformation as a transformation from elements of S to that part of T, which is phi S, to elements of that part of T, which is phi S. It seems to be a little bit different here in chapter 4. So let me just clear a little bit of space. So in this case, how can I say it? Phi here is not necessarily to be considered as similar or dissimilar. So it may be that we've got S again, and we've got a system, he uses Z here. And then we've got phi S, which is a part, or potentially a proper part, or maybe even identical with Z, but whatever. And we've got this transformation phi, which may be a similar transformation, maybe as he says, a dissimilar transformation, which clearly means not similar. So we can either consider this transformation phi as a transformation between taking elements of S, and the transforms of those elements are going to be elements in phi S. Or now he seems to introduce some terminology which allows us to talk about the transformation as if it's a transformation from the system S to a part of the system Z. Okay, so this it seems to be a bit in many ways it might seem to be unnecessary, all of this terminology, considering from maybe a modern perspective how we tend to think about these things. It might seem that there's a much more obvious way that we can talk about these kinds of ideas in a much more clear way. But as I've emphasized in previous videos, the ideas that are being introduced here were kind of in their very in a very kind of primitive form. So the ideas being introduced were in a way being introduced almost for the first time in some cases. So they hadn't gone through, the ideas hadn't been through that process of refinement to get to the stage that we're at now with modern mathematics, where we're talking about functions and maps between sets and things like this, which is very refined and very efficient and much clearer. Here there's it can seem that it's kind of a bit, it can almost seem a bit muddle-headed really to us. And that's not me trying to suggest that Dedekind didn't know what he was talking about or anything like that. It's just, I think because there was such a lack of clarity about these concepts that have been taught, these systems and transformations between systems and things like this. There was such a lack of clarity on what was going on here at this stage that really Dedekind did a very good job to in introducing these ideas and trying to present them in an understandable way. You can't, it's not necessarily, I would imagine it's not necessarily easy to really articulate ideas that haven't been articulated before. Okay, so anyway, that's just what I wanted to say about this. Let me get rid of that, so it's not really important. So where was I? I cut myself off, didn't I? Hence we call phi a transformation of the system S in itself, when phi S is a part of S. Okay, so I've put it off now, haven't I? But we had S, and we have the transformation from S to phi S. where phi s was considered a part of some system Z, uppercase Z, but now we're considering the specific case when Z is actually S. And when we've got a situation like this, then this is what's called phi. We call phi in this case a transformation of S in itself. And we propose in this paragraph to investigate the general laws of such a transformation phi. In doing this, we shall use the same notations as in chapter 2, and again put phi s equals s primed, phi t equals t primed. So remember, this primed notation seems to be reserved for when we're using the symbol phi for our transformation. We use instead of phi s, we might use s primed as a shorthand notation, and phi t in the case of a system will be t primed. However, if we've got a transformation that we call in psi, for example, as I've pointed out in the last video, I don't recall any part of the work where psi s, beg your pardon, psi s is abbreviated to s primed. So let me put some exclamation marks around that, because I've not seen this from memory. I've not seen this anywhere in Dedekind's work. The primed notation seems to be, for whatever reason, reserved for when we're talking about the phi, when we're using the symbol phi as the transformation. There are other transformations, symbols that are used for transformations. Psi, chi is used, for example, but phi seems to be the kind of de facto symbol for a transformation. Okay, so these transforms s primed, t primed are by 22 and 7 themselves again elements or parts of s, like all things designated by italic letters. So these transform, right? So remember this, we've got this relation of part designated by this. I mean, I don't really know what the symbol's called. It looks like a kind of backwards. Sorry, not a backwards. It looks like a 3. It's not a 3. I'm pretty sure it's not a 3, but so I don't really know what to call it. So I'm just going to call it the part symbol or part or something like that. So this applies to. Remember, we've got some. We can consider single elements as systems. So as I discussed in the first video, a system which has a single element is identified with that single element. There's no distinction between a system that contains a single element and the element that is the only element of that particular system. And this part relation applies equally well to systems with one element as it does to systems with more than one element. So, for example, if I want to say that lowercase s is an element, or the element lowercase s is an element of the system uppercase s, I can write this. If I want to say that the system T is a part of the system S, I write this. Okay, so it's the same symbol. Again, you got to bear in mind that these ideas were in their very early stages. So whereas now, typically when we deal with set theory, we have two. We often have at least two notions of two relations of part to whole. One to express that such and such is an element of this set, and one to express that this set is a subset of this set. There's no such distinction here. So we use the same symbol, whether we want to express that S is an element of the system S, or whether T is a part of the system S. So, in particular, if S is an element of the system S, then phi S, which equals S prime, is an element of the system phi uppercase S, which in turn is a part of the system S, and therefore S primed by 7. Is that the one that's referenced? Yeah. Theorem 7, S primed is an element of S. And similarly, running out of space, if we've got phi of T, the system T, which is T primed, this is a part of S also. Yeah. Okay, so definition 37. K is called a chain when K primed, the transform of K, is a part of K. We remark expressly that this name, this is really important actually, we remark expressly that this name does not in itself belong to the part K of the system S, but is given only with respect to the particular transformation phi. With reference to another transformation of the system S in itself, K can very well not be a chain. So this is really important, that to describe a system K as a chain, arguably this is not an adjective, so to speak, that applies directly to the system. It's more to do with the system and the transformation, with reference to a particular transformation. So if we say that K is a chain, we're not really just talking about, just like in group theory, for example, we might say, oh, G is a group. Well, actually, there's a bit more information to it. It's a very common thing to do to say G is a group, but we've got to bear in mind that for something to be a group, there's always got to be a certain binary operation defined on the elements of that group. Okay, so to say that K is a chain is only kind of half of the story, in the same way that saying that G is a group is only half of the story. It's really G along with such and such a binary operation is a group. So K along with a particular transformation is a chain. Okay, and as it says, with reference to another transformation of the system S in itself, K can very well not be a chain. So what we need for a chain is we need a transformation of a system within itself, and there is a part of that system K such that K primed, which is the transform of K with respect to this particular operation, is a part of K. Okay. So then on to theorem 38. S is a chain. This is kind of obvious, really. So S is a chain because any transformation of S in itself will satisfy the relevant condition for S to be a chain. Namely, if we've got a transformation from S to phi S, which if the transformation phi is a transformation of S within itself, then phi S is a part of S. But remember that phi S is S primed. So in other words, we've got S primed is part of S. So in other words, we can choose any transformation of S in itself, and that will yield the result that S is a chain with respect to that transformation. These first few theorems, by the way, are fairly straightforward. Once we get up to theorem 59, they're a bit more involved. 59 to 63, and the last theorem of this chapter, theorem 63, is one that Dedekind actually doesn't prove in this. He leaves it for the reader to do. In other words, me in this case, or you in your case. So I've got a proof of theorem 63, which I plan to go through. It's not terribly difficult, but just to kind of complete the picture. So, okay, where are we up to? Theorem 30 or 39. The transform K primed of a chain K is a chain. Okay, so if K is a chain, then we know that K primed is a part of K. By 22, is it? Yeah, theorem 22. K primed is a part of K. That means that the transform of K primed is a part of the transform of K. And that's it. That's it, yeah. It's as easy as that. This says that the transform of K primed is also a chain. Because it's we've got a transform of phi, can be thought of as a transform of K primed to itself, I guess. Anyway, it's that's it. There's really nothing to it. Okay, so theorem 40. If A is a part of a chain K, then also A primed is a part of K. Again, it's another straightforward one to do. We've got A is a part of K. Then by theorem 22, A primed is a part of K primed. But K primed, because K is a chain, is part of K, and therefore by theorem 7, A primed is part of K. Easy. Theorem 41. Okay, so this one's a little bit, can seem a little bit strange, I guess. It is used a couple of times. So, where is it used? Theorems 57 and 58. It's used in the proofs of theorems 57 and 58. So, theorem 41. Here we are. If the transform A primed is part of a chain L, so A primed is part of a chain L, then there is a chain K. Remember, this is all with respect to a particular transformation, which may be similar or dissimilar, which satisfies the conditions. A is a part of K, and K primed is a part of L, and the system compounded of A and L is just such a chain K. So notice it doesn't say that K is a unique chain. It just says there is a chain K which satisfies these conditions, and this system compounded of A and L is one such chain which satisfies those conditions, but not necessarily the only chain. I doubt it is a unique chain. I doubt it. I imagine that there will be other possibilities, but I haven't proved that, to be honest with you. But I just my instincts tell me that it's if it was unique, then I think Dedekind would have proved that it's going to be unique. But I don't think there's any need for uniqueness here. Okay, so the proof, if we actually put K equal to the system compounded of A and L, then by 9, one condition is fulfilled, namely A is a part of K, because remember, if we've got a system compounded of A, B, C, and so on, then A is a part of that compounded system, B is a part of that compounded system, and so on and so forth. So here we've got K is equal to the system compounded of A and L, so A is a part of this system, this compounded system, and also L. L is worth bearing in mind that L is also a part of this system. We don't need that right now, but we will need it shortly. So that's the first condition fulfilled. Since further by 23, K primed is equal to the system compounded of, so that the transform of K is equal to the system compounded of the transforms of A and L respectively. So this was proved in, I went through this in, where was 23? Which video was that? That would have been video 2. So I'm not going to go through that again. And by hypothesis, A primed, or the transform of A, is a part of L. So that's by hypothesis here. By hypothesis, L primed, and L is a chain. So in other words, we've got that L primed is a part of L. Okay, so we can see how all of these hypotheses are necessary here. So what do we have? We've got A primed is a part of L, L primed is a part of L. So that means that K primed, not K primed. Yeah, K prime. This is also going to be a part of L. So that's from 10, theorem 10 apparently. Let me just double check. Yeah, ABC are parts of a system S, then the system compounded of ABC is a part of S. So A primed is a part of L, L primed is a part of L, so the system compounded of A primed and L primed will be part of L. So therefore, K primed is a part of L, which is that second condition there, satisfied. Hence it follows, because by 9, L is a part of K, so that follows from the definition of K. Remember, we've got A is a part of K, we've also got L is a part of K. That also K primed is a part of K. We've just shown that K primed is part of L. We've got L is a part of K, and therefore by 7, theorem 7, K primed is a part of K, and hence K is a chain, which was to be proved. Okay, so again, there's nothing suggesting here that K is the only chain that is going to satisfy these conditions. I'm not going to go into more detail with that. Like I say, I've not actually investigated that any further. If you are interested, then have a go yourself. See if you can prove it. Just while I'm clearing the screen here, I'd be really grateful if you would consider subscribing to the channel, hitting the like button, and leaving a nice positive comment in the comments section. And on that note, we will continue to theorem 42. A system M compounded simply out of chains A, B, C, and so on is a chain. So I don't really know what this adjective simply means here. I've not seen this anywhere else. Looking back to the definition, where was it? Definition 8. We've got a definition of a system compounded out of the systems A, B, C, but not compounded simply out of chains A, B, C. But there doesn't seem to be any distinction as far as I can tell. So compounded and compounded simply seem to be synonymous. I don't know where this word simply comes from, what it's referring to, whether it's something that has been translated from the original German, or whether it's something that's been added during translation. I don't know, okay? But it doesn't seem to... We could effectively just ignore it, and it doesn't seem that it changes anything. Okay, so since by 23, so the system compounded, forget about the word simply, compounded out of ABC, which we're calling M here. Then by 23, the transform of M is equal to the system compounded of the individual transforms of A, B, C, and so on. And by hypothesis, because A, B, C are assumed to be chains, we have that A... There is a typographical error here, by the way, where it says here A primed... the transform of A is a part of B. That should be a part of A. So it should be A... The transform of A is a part of A, not B. The transform of B is a part of B. The transform of C is part of C, and so on and so forth. So therefore, by 12, the system compounded of A primed, B primed, C primed is a part of the system compounded of A, B, C, and therefore M is a chain by definition. Okay, theorem 43. The community G of chains A, B, C is a chain. So since by 17, G, so the community G of chains G of A, B, C, and so on. Since by 17, G is a common part of A, B, and C. That's by definition. So this is G. So G is a part of A, and G is a part of B, and so on. Therefore, by 22, because if we apply 22 to each of these, what we get is that the transform of G is a part of the transform of A, the transform of G is a part of the transform of B, and so on and so forth. And therefore, G primed is the transform of G is a common part of each of the A primed, B primed, C primed, and therefore G primed must be a part of the community of A prime, B prime, and C prime by 18, apparently. Let me just double check. Every common part ABC, every common part of ABC is a part of the community of ABC. So G primed is a common part of A prime, B prime, C primed, and therefore must be a part of the community of A primed, B primed, C primed. Where was I? Oh, right. Okay, so no, we're not done yet. Is also common part of, then by 7, G common part of, by hypothesis, A primed. Aha, okay, so actually I've got a bit ahead of myself. So because we know that A prime, because A, B, C, these are all by assumption chains, then we've got A primed is part of A. B primed is a part of B. So by 7, theorem 7, we've got that G primed is a part of A. G primed is a part of B. So effectively putting together these two and applying theorem 7, and then the next two and applying theorem 7. So therefore, G primed is actually, it's not only a part of the community of A primed, B primed. In fact, we kind of proved that, haven't we? Actually, that was theorem 23. G primed is a common part of A, B, C, and so on, and therefore, by theorem 18. G primed is also a part of the community of ABC. Part of the community of ABC by theorem 18, which was to be proved. So in other words, we've shown that G primed is a part of G. Remember, the community of ABC we defined to be G, so we end up with G primed is a part of G, and hence is a chain by definition. 44. Okay, so we're on to a definition now, so I'm going to go on to the next page. If A is any part of S, we will denote by A sub 0, just like Mortal Kombat. The community of all those chains, example S, of which A is a part. This community A0 exists because A is itself common part of all these chains. Okay, well, the community of all those chains of which A is a part, well, I mean, A is a part of S, and S is forced to be a chain with respect to any transformation of S within itself. So we can always talk about A0. There's always going to be at least one chain, and A is a part of S. And since S is a chain, that means that there's always going to be at least one chain. This community A0 exists because A is itself common part of all these chains. Since further by 43, A0 is a chain, we will call A0 the chain of the system A. Remember, this is with respect to a particular transformation. For a given system A, which is a part of S, with respect to different transformations, we may get different chains corresponding to A. The chain of the system A may be different with respect to different. In fact, it will in general be different with respect to different transformations. So we will call A0 the chain of the system A, or briefly the chain of A. This definition too is strictly related to the fundamental determinate transformation phi of the system S in itself. And if later, for the sake of clearness, it is necessary, we shall at pleasure use the symbol phi naught A instead of A0. That's really useful, actually, that notation, because the problem with this notation A0 is that it doesn't emphasize the transformation that this is with respect to. So phi naught A is sometimes used instead of A0 when there's maybe a need to emphasize the transformation. And this notation, by the way, is a bit more general. So A0 will typically, just like the S prime and T prime and things like that, will be used as shorthand when we've got in mind a transformation which is represented using the symbol phi. If we use a different symbol, psi, for example, it is psi, yeah. We will stick with the notation psi naught of A instead of writing A0. We typically won't write that. We'll write psi naught of A. And we'll see this in chapters further down the line, chapter 8, I think. Somewhere anyway. Somewhere around chapter 8 or chapter 9 or something like that. Yeah, chapter 8. I can see it in chapter 8. Now, this, just to dwell on this a little bit longer, this phi naught can itself be considered in many ways as a transformation. So we can consider it as the transformation which takes the system A, which transforms the system A into the system A sub naught, arguably. If we want to think about it in that way. A is just any part of a system S. Okay, so we could form, there's no reason, as far as I can see, why we can't do this. We could have, for a system S, we could form a new system from this, which is the system of all parts of S. Not necessarily proper parts, the system of all parts of S. So, and then we could, this phi naught would be a transformation effectively from from parts of S to its respective chain, which would be another part of S. So this would be another, arguably, a transformation of a system within itself, I guess. I actually haven't thought about it. This is the first, I've not thought about it in that much detail. But yeah, I think that would make phi naught in that case kind of like another transformation of a system within itself, but a different system, the system of all parts of the system S. It's never used. I don't think that idea is ever used in here, but not explicitly. But it's interesting to think that. And likewise, designate the chain of A corresponding to another transformation, omega, by omega sub naught or sub 0 A. So that's effectively what I was saying there with respect to a different transformation. For this very important notion, the following theorems hold true. So this the chain of the system A is kind of like a minimal chain which contains A as a part. So we've it's the next theorem actually. It's kind of, it follows immediately from the definition that A is a part of A naught. So A naught, because it's the community, the common part of all of the chains. So we're considering all possible chains which have A as a part. We're taking the community. So this is kind of a minimal, it's going to be the minimal chain, really. Because there could be a lot of, if we take a chain, for example, there could be all sorts of kind of superfluous bits to the chain. So again, just to dwell on this a little bit longer. What we'll find is further in the work that an example of a chain is effectively the sequence of natural numbers. So we've got one, starting with one. Okay, well, I'll call it 2. Why not? 1, 2, 3, 4, and so on and so forth. Okay, so this would kind of be, this would be a chain corresponding to the element 1 in the system, what Dedekind calls the system N. But it might be that there's all, to this we could have another kind of parallel sequence. We could have A and A primed, and then A primed primed, and A primed primed primed, for instance. So we get this other kind of sequence, so to speak, of elements. And we can kind of jam these together, right? But really this has nothing to do with the chain corresponding to this element 1. Okay, so the elements 1, 2, 3, 4, and so on and so forth, and then A primed, A prime primed, A prime prime primed. Jamming these together, these all form a chain for the element 1, but there's kind of this superfluous bit. So what this does, by taking the community of all of the possible chains, we kind of get everything down to the bare minimum. It's like a minimal chain. So what will happen in this case is all of these the bits of this chain that are superfluous, that don't appear in every other chain. In other words, they're kind of not essential really, in a certain respect. They get stripped away, and what we're just left with is this kind of minimal chain. Okay, so theorem 45, it's kind of obvious really. For A is common part of all those chains whose community is A0. So in other words, remember A0 is the community of which symbols shall I use? I can't use A, so B, C, D, where B, C, D are all chains in the system S for which A is a part. So A is a part of B, A is a part of C, A is a part of D. So therefore A is a common part yeah, so A is a part of each of these, and therefore A must be a part of the community by theorem 18. 46th theorem, the transform of the chain of A is a part of the chain of A. Okay, so where does this come from? For by 44, A0 is a chain. 44, if A is any part of, so A0 is a part of, sorry, A is a part of A0. So therefore, oh, hang on a second. Yeah, sorry. So therefore, since A0 is a chain, sorry, we're getting just a little bit lost here. By definition 44, A0 is a chain. I don't actually need the A as a part of A0. Yeah. A0 is a chain by definition, and therefore the transform of A0 must necessarily be a part of A0. Okay, so it kind of follows immediately, actually. I was reading too much into it, overthinking it. So theorem 47, if A is part of a chain K, then also A0 is a part of, right? So A is a part of K. K is a chain. So therefore, by theorem 22, the transform of A is a part of the transform of K. But the transform of K, because K is a chain, is part of K, and therefore A primed is a part of K. No, that's not what I needed to do at all, is it? A is a part of K. I've proved something completely irrelevant. If A is part, A naught is the community and hence also a common part of all the chains. Right, okay, right. So K is a chain which contains A as a part. Okay, so yeah. So A naught is by definition a part of K. There's actually nothing to prove there. Getting a bit carried away again. So 48, remark. One can easily convince himself that the notion of the chain A naught defined in 44 is completely characterized by the preceding theorems. 45, 46, 47. Okay, whatever. 49. Theorem A primed is a part of A naught primed. Well, okay, so by 45 we've got that A is a part of A naught. By theorem 22, A primed therefore is a part of A naught primed. Okay, on to the next page, on to theorem 50. How are we doing for time? A primed is a part of A naught. So what have we just proved? A primed is a part of A naught primed, but because A naught is a chain, that's a part of A naught, and therefore A primed, the transform of A, is a part of A naught. Theorem 51, if A is a chain, then A naught is equal to A. Proof, since A is part of the chain A. Yeah, okay, so we know from theorem 4 that A is a part of A. So if A is a chain, then A is a part of the chain A. And by 47, what's 47? A is part of a chain K, right? So then A naught is a part of A. And what are we trying to put? Oh, yeah. So that's one half of what we need. And then on the other hand, from 45, we have that A is a part of A naught. And therefore, by theorem 5, we've got that A is equal to A naught, or A naught equals A, whichever. Theorem, if B is a part of A, then B is part of the chain of A. So, well, this follows from the fact that A is a part of A naught. So if we've got that B is a part of A, and by theorem 45, A is a part of A naught, excuse me, it follows by theorem 7 that B is a part of A naught. Easy. And conversely, right, okay, so and conversely, so oh no, sorry, that's theorem 53. I'm jumping ahead of myself. So on to theorem 53. If B is a part of A naught, then B naught is a part of A naught, and conversely. Okay, so what does it say here? Because A naught is a chain, then by 47, from B is a part of A naught, then it follows that B naught is a part of A naught. Conversely, if B naught is a part of A naught, then by 7, we also get B is a part of A naught, right? Because we know that B is a part of B naught. And if we're assuming now, So we're trying to prove in this direction. B naught is a part of A naught. Then it follows by 7 that B is a part of A naught. And that's it. Okay. Right, okay. Easy. Sometimes expecting a little bit more, and it's surprising sometimes how straightforward the proofs actually are. So theorem 54: if B is a part of A, then the chain of B is a part of the chain of A. This follows from 52 and 53. If B is a part of, right, so yeah, 52, we've got if B is a part of A, then B is a part of A naught. And then theorem 53, if B is a part of A naught, then B naught is a part of A naught. So it just follows immediately. Theorem 55, if B is a part of A naught, then is also B primed a part of A naught. So B is a part of A naught. By theorem 22, we've got B primed is a part of A naught primed. But A naught is a chain. So therefore, A naught primed, the transform of A naught is a part of A naught, and therefore B primed is part of A naught. By 53. Yeah. Okay. Oh, okay. So it's actually given two different ways. I've gone for the second way apparently. Yeah. The same result as is easily seen can be obtained from 22, 46. So I've used 22 to go from here to here, 46 to go from here to here, and then 7 to go from to get B primed is a part of A naught. So there's different ways. Different ways that you can go about these proofs. Where are we? 56. If B is a part of A naught, then the transform of B naught is, okay, this follows from 53. Because B is a part of A naught, then B naught is a part of A naught, then apply theorem 22. The transform of B naught is part of the transform of A naught. 57. Theorem and definition. Okay, so A naught primed equals, so this is the theorem part. So we're on to 57 now. Theorem and definition. So A naught primed is equal to A primed naught. So these are not the same thing at all. Necessarily, I mean. It turns out that they are, but they're not necessarily. We can't just assume that due to the similarity of the notation that these must be the same thing. It turns out they are, and the definition is effectively that we will call this just A naught primed. Okay, so A naught primed is equal to A primed naught, i.e. the transform of the chain of A is at the same time the chain of the transform of A. Hence, we can designate this system in short by A primed naught. So that's the definition part. Okay. And at pleasure call it the chain transform or transform chain of A. So these will be used interchangeably. There are some occasions throughout where this symbol is used, and to really understand the proof, I'm trying to find it now. I can't find it, but there are some examples which I'll get to eventually as I go through. it really does help if you interpret this in either this way or this way in a particular instance. So this notation, this a primes naught without the brackets is useful, but it can be a little bit ambiguous in some cases, where it is kind of necessary to really understand the proof properly to interpret in one or the other of these particular ways. We'll come to it eventually in the whichever video. With the clearer notation given in 44, the theorem might be expressed by phi of phi naught a equals phi naught phi of a. So yeah, instead of so this a naught in brackets primed would be phi of phi naught a, and the a primed sub naught is going to be phi of a naught. No, that's not right, is it? So we're using the phi notation. Okay, I need a bit more space. It's phi of a, that's the a primed, and then we've got phi naught, and it's we've got equality between these two. So if for brevity, go on to the next page, if for brevity we put a primed in brackets naught equal to L, L is a chain, basically by definition, and by 45, a primed, the transform of a is a part of L. So that's due to, if it's 45, then that means that we're using that a primed, the transform of a is a part of a primed naught. But remember, this is just L. Okay, so that's where we get this from. Hence, by 41, there exists a chain K, right, okay, so remember one of the conditions with 41 was we've got that the transform A primed is part of a chain L. So the notation here is being specifically introduced to make it easier to match up with theorem 41. So this was what, yeah, I said earlier that theorem 41 is used in the proof of 57 and 58. So hence there exists a chain satisfying the conditions A is a part of K and K primed. The transform of K is a part of L. Hence from 47, what's 47? A is a part of a chain K. Then is also A naught a part of K. Okay, so by 47 we get that A naught is a part of K. And therefore, by 22, A naught primed is a part of K primed, and hence by 7, since K primed is a part of L, then we get that A naught primed is a part of L. Remember that L was equal to A primed naught. So we've got one. We've got one of the. We've shown that one of these is a part of the other. So A naught in brackets primed is a part of A primed naught. Now we need to show that show the other way, that this A primed in brackets naught is a part of A naught in brackets primed. Okay, so let's do that. So how does that go? So since further by 49, A primed is a part of A naught primed. So what's 49? Yeah, so that's straight from theorem 49. And by 44, A0 primed, and 39, A0 primed, right, so because A0 is a chain, and the transform of a chain is a chain. That's theorem 39, right? The transform K primed of a chain K is, right, so A0 primed is a chain. Then by 47 also, oh right, yeah, okay, so the chain, because this is a chain, because A primed is a part of that chain, then the chain of A primed must also be a part. So A primed in brackets naught is a part of A naught primed, which is the other, shows that it's the other inclusion, I guess. So we've got both inclusions, this and this, and therefore by theorem 5, sorry, we get equality. In other words, A naught primed is equal to A primed naught, which is what we needed to prove. Theorem 58. So if A naught, so I'll just clear this and we'll go through theorem 58, and then I'm going to finish this video there. If you haven't done so already, then please feel free to subscribe to the channel, hit the like button, and leave any suggestions that you might have about things that you'd like me to have a look at on this channel. Anything that you think might be interesting to take a look at. Okay, so theorem 58. A naught is equal to the system compounded of A and A naught primed, i.e. the chain of A, which is this, is compounded out of A and the transform chain of A. For brevity, we again put, in fact, right, this is what I was talking about actually. I thought it was further into the book, but it's this theorem where it's useful at certain places to interpret L, what we're going to define as L, which is A primed naught without any brackets, to interpret it as either A naught primed or A primed brackets naught, depending on the particular set of circumstances. And we put K equal to the system compounded of A and L. Then by 45, which I can't remember off the top of my head, A is a part of A naught. A primed. Right, so here, if we view L as A primed naught, then because we've got that A primed is a part of A primed naught, it follows that A primed is a part of L. So it helps if I'm going to apply theorem 45 there, that I'm interpreting L specifically as A primed in brackets naught in that case. Arguably, I don't have to necessarily, but it just helps. And since L is a chain, by 41, by 41, what's 41? Aha, okay, so this K here that we've defined, oh no, so sorry, L is a chain by 44, because it's defined to be the chain of the transform of A, right? The chain transform or transform chain of A. So L is by definition 44 a chain, but by theorem 41 because we've got all of the conditions satisfied for theorem 41, then the way that we've defined K means that K is also a chain. Okay, so A primed is a part of L, and we've also got that A is a part of K, satisfied, and presumably we'll have that K primed is a part of L. Okay, which I'm not going to check now, but presumably we've got K primed is part of L as well. L is a chain. The same thing is true of K. So K is a chain. Since further A is a part of K, so yeah, because A is it's one of the systems that K is compounded out of. So by theorem 9, A is a part of K. Therefore, by 47, the chain of A is part of K. Remember, K is a chain. On the other hand, so that's one of the, that's part of what we need. On the other hand, since by 45, A is a part of A0, and by 46, also L, which we're interpreting here as A0 primed is a part of A0. Apparently that's theorem 46. Just let me check. Yep. So again, here I'm interpreting the L as A0 primed here to apply theorem 46. So from this we get that L is a part of A0. Then by 10, what's 10? Oh, right. So A is a part of A0 and L is a part of A0. So therefore, the system compounded of A and L will also be a part of A0. In other words, the system compounded of A and L, which is K, is a part of A0. And hence, K is equal to A0. So K was the system compounded of A and L. But remember, L is A prime naught. So in other words, we get the system compounded of A and A prime naught is equal to A naught, which is what we needed to prove. Yeah, so it's theorem 5 applied to A0 is a part of K and K is a part of A0. And that's it. Okay, so we're done for this video. We're not done with this chapter. There's quite a lot more for me to go through in this chapter, which I'm going to leave for the next video. So I'm going to split this chapter into 2 parts. As usual, if there's anything that I've said in this video that you didn't quite understand, that I didn't explain very clearly, please feel free to ask any questions that you have in the comments section. Or if you want to contact me directly, please feel free to do so. I'm always happy to help. Thank you for watching, if you've made it this far into the video, and I will look forward to seeing you in the next video.